Thank you. Thank you very much. Everybody sees well. This will be an old-fashioned blackboard talk. Let me, thank you. Let me thank warmly the organizers for this wonderful event and this so nice atmosphere in the tent. Let me comment about École Polytechnique and École Normale Supérieure. You know, the former students of École Polytechnique and former students of École Normale Supérieure have a common point. They only say l'école when referring to their alma mater. No need to make precise which it is. For them, it is obvious there is just one. And next comment is I appreciated very much all the detail of organization. When I arrived at the hotel yesterday, I noticed I was put in room 314, the Pi room. This made my day. Okay, thank you very much. So today will be about optimal transport and geometry. It's a subject on which I have worked for a long time, and I wrote two books, especially the second book was in large part about this. It will be mainly an introduction to the subject, and I will report on recent results but not go into technicalities. Let me mention that this place, Bonn, was very important for the development of this subject, with people like Felix Otto, Karl Theodor Sturm, and other people around. This was one of the centers in which the theory as it is now was developed. And let's start by motivating the subject about the difference between what we shall call analytic point of view and synthetic point of view. These are, in many fields of mathematics involving computations in one way or the other, you have a dichotomy between these 2 points of view, which is easy to understand on concrete example, which is a notion of convexity. What does it mean for a function to be convex? Let me give two definitions. So let phi be a function from Rn to R or whatever. And let's say that the function is convex if its Hessian is non-negative. Okay. And let's say that the function is convex if you have the usual convexity inequality, phi of 1 minus tx plus ty is bounded above by 1 minus t phi of x plus t phi of y. And this for any x, any y, and any t between 0 and 1. As we know, these two definitions are equivalent, at least if phi has some smoothness. But they are very different in spirit. Left-hand side, we are computing something, some object related to phi, namely the second derivative, and at each point, there is a value which is associated to this. Here, we are not computing anything. We are just expressing some geometric property of the graph of phi, namely the fact that it always lies below the chord. So here, let's call this synthetic. It's about properties of the object. And here, analytic, we are computing something which is related to the object. These two definitions are very different in their immediate consequences. This is obviously a local definition. This is not. You have to check it for any x, any y. And in practice, you can never check it. If I give you a function with a complicated expression, and you try to establish this to prove that it is convex, usually it will fail. But this has a chance to work. So this is more effective. And also, this, on the other hand, is more general. Of course, if I give you absolute value of x, you don't know what this means, but this is perfectly well defined. And so, a priori, you have a wider class of objects on the right-hand side. Also, this definition is very useful. We use it all the time when we are using convex functionals, functions, and so on. And part of your job as an analyst consists in checking convexity using this and applying using that. So this is very useful. And my last comment is that this is very stable. Imagine you have a sequence of functions, phi k, for k an integer. and converging to something. And you want to prove that the limit is convex if the elements in the sequence are all convex. How do you do? Well, if you try to apply this definition, you are doomed, except if you know that second derivatives converge. Very strong notion of convergence. If you apply this definition, it's so easy. All you need to know is pointwise convergence, not even uniform. So it's much more stable, the second definition. These are general properties of this analytic versus synthetic side, and it's part of the power of the convexity concept that you can go from one to the other. There is another field of mathematics in which we are exposed to this dichotomy very early, like in, when you are maybe 12 years old or 13 or 14, depends. This is when you do Euclidean geometry in school. And in Euclidean geometry, as you learn, there are two main ways to do the geometry. You can do it in synthetic way, in the Greek style, with properties of the circles and lines and triangles and axioms, as Euclid did more than 2,000 years ago. Or you can do it in analytic way, using equations. So circles will be something like x squared plus y squared is something. A line would be something like ax plus by plus c equals 0, etc. And this often leads to the result more systematically. It's more effective. But with this, it's very useful, and often you have the impression that you understand better through this, the reason why something works or doesn't work. And of course, the 2 points of view are equivalent, but it's good to have both in store. Now, let's go for another concept, which is non-Euclidean geometry. How to do non-Euclidean geometry? Basic concept in non-Euclidean geometry is the curvature. And here again, as people figured out long ago, it was useful to have both an analytic and a synthetic approach to curvature. Say the Gauss curvature for some surface. How do we define the Gauss curvature in an analytic way? There are several ways to do this. You can do it using some formulas involving the Riemannian metric and so on. Here is a definition which I like is, if you take two unit vectors, u and v, starting from some point x, at some point x, and you start two geodesics, one with initial velocity u, the other with initial velocity v. So you have these two geodesics which start orthogonally immediately, and you ask which is the distance between your two geodesics as time goes. So initially it is 0, then it increases, and you may compute that the distance between the first geodesic and the second geodesic is something like square root of 2 times t times 1 minus some coefficient, which I will write kappa over 12 t squared, plus higher order terms as t is small. This kappa here is the Gauss curvature, or if you want, the sectional curvature associated with the vectors u and v. So here you see, it is defined as some coefficient in the expansion or some second derivative of something, but here this formula allows you to give a definition by computing. Say you compute the distance doing some expansion and you get the result of what is the curvature. This would be an analytic point of view. By the way, stated in this form, you immediately see that the curvature is an isometric invariant because it only depends on the Riemannian distance. And now what would be a synthetic point of view? So in synthetic approach, the one that was developed and most successful for this, for curvature, so this will be about kappa equals the Gauss curvature, is the approach of Cartan, Alexandrov, Toponogov, usually denoted by CAT, Cartan, Alexandrov, Toponogov, in which you don't try to define synthetically the notion of curvature, but rather to use a comparison to say, for instance, that curvature is non-negative if and only if such property is true. In the same way that you say here, you don't try to define the second order derivative, but you say a function is convex if and only if you have this. And in this case, for Cartan-Alexandrov Toponogov, for instance, it will be kappa is non-negative if and only if triangles are fat. Triangles, so fat triangles. What does it mean, fat triangles? Okay, this is a geodesic triangle. Here it's obvious the way I drew it that it is fat. But if you want to quantify this, you say, okay, let's draw the median from here to here. And let's compare this to the median of a triangle which has the same length but which is drawn on the plane. And if the median here is longer than the median of the triangle which is isometric but which is flat, then you say that this guy is fatter than this guy. As I always tell my students, if this is the individual, this is the neck, this is the belt, this is the tie, it goes from the neck to the middle of the belt, and the bigger you are, let's say, the longer your tie should be so that it exactly goes to the middle of the belt. This is how you understand fat triangles. So you see here, we did not define any curvature, but we define what it is to have curvature bounded below. It's a comparison approach by reference to the reference space of zero curvature, which is the plane. And similarly, you can define what it is to have curvature bounded below by 1, bounded above by 1, whatever, by playing on the shape of triangles and the way they are. So this is for sectional curvature. And now comes the problem, which will be of interest in this talk. What about now Ricci curvature? So Ricci curvature is, after sectional curvature, another one of the most, let's say, one of the three most popular notions of curvature. And it's the curvature which is preferred by people working in probability theory in geometric context. Whenever you have a problem which mixes volumes and gradients and length, you can be sure if it is non-Euclidean, Ricci curvature will play a role. So it will be interesting to understand it both from analytic and synthetic point of view. And let us go to this. So from now on, we switch to only Ricci curvature. And we ask ourselves, what does it mean, analytic theory of Ricci curvature, synthetic theory of Ricci curvature? So first, let's give a definition. There are several possible definitions for analytic definitions of Ricci curvature. Here's a simple one. Here's your point x. Give yourself a unit vector, u, and then you complement this with some orthonormal basis, say E2, E3, etc., so that u is the same as E1. And this should be an orthonormal basis of the tangent space at x. Oops, do you see when I write here, people? You have to complain, my friends. Here better? Yes, there is a lot of room here. Yeah. And here is okay. Okay, super. So I take here an orthonormal basis, E1, etc., En, orthonormal, and I will define the Ricci curvature in the direction E1 to be the sum of the sectional curvatures, let's write them kappa, in direction E1, Ej, for all j bigger than 1. So it's a sum of Ricci, of the sectional curvatures. And it turns out that this can be extended into a quadratic form. Another way to express Ricci curvature is to look at evolution of volumes. Just a moment ago, I told you about sectional curvature as measuring the infinitesimal distortion of distances. Now, Ricci is about volumes. Here is one possible way to express it. You look at the volume element of in your Riemannian manifolds. say, around the point x. And let's assume you do this in geodesic coordinates centered at x. And then, at first approximation, it will be like the usual Euclidean volume, dx. But then there will be a correction, and the first correction is something like minus 1 over 6 Ricci. Let's write Rij for the coefficients, for the components of the Ricci tensor, xi, xj, plus some lower order term, some higher order term, sorry, in terms of x dx, when x is approximately equal to 0. So you see, it tells you about the infinitesimal distortion of the volume with respect to the Euclidean volume. When the Ricci curvature is positive, it is smaller than expected. When the Ricci curvature is negative, it will be bigger than expected. This, again, is an analytic definition, and you can use it in computations, and there are formulas to compute the Ricci curvature depending on the metric. So if I give you a metric, you can compute its Ricci curvature and check, for instance, if it is non-negative as a quadratic form. And now you ask, what would be a synthetic point of view on the Ricci curvature? And this question stood open for quite some time, but it was known for a long time that there are many interesting consequences, global consequences of Ricci curvature bounds. For instance, first, often these bounds appear through analytic type inequalities of the following type, and always dimension and curvature bounds were mixed together. Curvature plus dimension bounds have many consequences. And often these are put together with the word CD, C for curvature, D for dimension, K the lower bound for the curvature, and the upper bound for the dimension. So this would be something like Ricci bounded below by K and dimension bounded above by N. And one way to express this in analytic terms is like minus gradient of minus gradient Laplace psi dot grad psi plus, I always get it confused, gradient of Laplace square of Laplace of grad square plus square over 2 blah 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 is bounded below by k grad psi square plus Laplace psi square divided by n. Okay, is a kind of inequality involving derivatives of order 3 in psi. Well, this is the natural Laplacian associated with the Riemannian structure, in which k and n appear naturally, and it was known that for various values of k and n, you can get many inequalities out of this inequality by integrating, by parts, doing all kind of transforms and so on. For instance, with this you can prove Sobolev inequalities, you can prove volume comparison inequalities, you can prove logarithmic Sobolev inequalities, many things. But this is not what you would call a synthetic property as you would like to express it in terms of distances and volumes. Here is another property now, which is a consequence of Ricci bounds, much closer to the spirit of what would be a synthetic property. Let's call it curved Brun-Minkowski. And this one will encapsulate much better than this, for instance, some meaning of Ricci curvature. And you will see it's about properties. So here is what it says. And let's write it only in the simplest case. If Ricci is bounded below by 0, and dimension is bounded above by capital N, so curvature dimension 0n, then you have the following. Whenever you take a set A in your manifold, some nice set. A set B in your manifold, some other nice set. And then you look at all the geodesics going from A to B. And you look at all the midpoints on these geodesics. This is the set of all midpoints of A and B. Let's call it M, like midpoint. Then if the volume of A is large and the volume of B is large, automatically the volume of M will be large. And more precisely, the volume of n to the power 1 over n will be bounded below by half of the volume of A to the power 1 over n plus B to the power 1 over n. So you see, this is very nice. It only depends on distances and volumes, and it encapsulates the property that if you have positive curvature, somehow there are many intermediate points. People working in positive curvature always have this kind of picture in their mind. This is the typical picture of geodesics in positively curved space, because geodesics typically have their separation distance, which increases less than geodesics in Euclidean space. So if you have to reach some specified target, at the intermediate times, you have to be rather spread, so that you have room to converge again. Diverge first, converge then. So this is encapsulated by this inequality that the volume of midpoints is bounded below to the power 1 over n, is bounded below by half of the volume to the power 1 over n plus the volume to the power 1 over n. Okay? So this is something that we very much like to call a synthetic property, but is not clear that it is equivalent to this. This implies this, however, some equivalence, this is not clear. By the way, this inequality was discovered only about 15 years ago, in contrast with the classical Brun-Minkowski inequality, which goes back to more than 100 years ago. And it was discovered during the development of I'd say during the exploration of the links between geometry and optimal transport. And more generally, somehow the solution to this problem, what should we put here as synthetic equivalent notion for Ricci curvature in the negative or bound on the Ricci curvature, was discovered almost accidentally while exploring properties of optimal transport and their relation to geometry. So far, let's say the introduction, and let's go now into optimal transport. To summarize, we know how to define sectional curvature in an analytic way, sectional curvature bounds in synthetic way. We know how to define Ricci curvature in an analytic way. We wonder how to define Ricci curvature in synthetic way. And there are some analytic inequalities. There are some inequalities involving volume and distance, but still not sure it's the right one. And we want some concept that will be equivalent to the classical notion of Ricci curvature bound. So let's go for it. And as I said, the solution to this problem came through the encounter of 4 different fields of mathematics. Let's review this briefly. So synthetic theory of Ricci curvature bounds. So it came from the merging, the encounter of 4 fields. And let's see which these 4 fields are. The first is curvature, as I explained to you. So Ricci curvature, and we explained some properties. The second one is the theory of gradient flows. Gradient flow is an evolution equation in which you are going in such a way as to make some quantity go down as fast as possible in some sense. And is defined by some equations like dx dt equals minus gradient E of x, where E is some kind of energy. You have this potential energy or whatever, and you make it decrease as fast as possible. And it appears about everywhere. And it's something like a dissipative counterpart of Hamiltonian flow. Hamiltonian is the archetype of conservative flow. Gradient flow is the archetype of dissipative flow. Third field is, let's call information theory. It is a bit pompous to call it this way, but still, which will be the study of functionals which are nonlinear integral functions of probability densities, with the most important of them being the information of Boltzmann and Shannon whenever you have a reference measure nu, and you have a reference, and you have mu, the measure whose information you want to quantify. You call it, you define it by integral of rho log rho d nu, where rho is the density of mu with respect to nu. This functional appears about everywhere in statistics, statistical physics. You find it in the so-called Sanoff theorem about large deviations of the empirical measure, like if you are observing the empirical measure associated to a sequence of independent, identically redistributed random variables, and you ask, which is the probability that this empirical measure, which is the average of the Dirac masses, is far from the true law according to which the random variables are drawn. And the answer is that the probability of a large, say more than a fixed number discrepancy is exponentially small. Exponential minus n times something, where n is the number of samples that you draw, and the something is precisely this. So it tells you in some sense about how difficult it is to reconstruct the law of a random signal from the observations. That is somehow the meaning behind it, and that's why you can call it information. This is for this field. There are other notions of information, in particular the so-called Fisher information, which is what you obtain when you make this dissipate along the heat equation and so on. And these quantities appear a lot in statistical mechanics, in communication theory, and so on. And the fourth field was optimal transport. Optimal transport is about the best way to transport things from initial location to final location. So let's assume you have some goods here at some initial locations, and you have some targets. And you want to transport the goods from the initial locations to the targets. Maybe there are factories here producing something, and you are shipping this to the shopping malls where the customers will buy them, or something like this. You know what each site produces, you know how much you want to put in each store, in each shopping mall, and then you ask, how do I do the matching? Do I send the material from here to here, or from here to here, etc.? It's kind of like finding the right permutation. And you can ask this problem in such a way that the total transportation cost is minimum, that you spend literally the least amount of money during this transport. I will write a precise mathematical formulation in a moment. And let us say that this optimal transport business started with Monge at the end of the 18th century, and that it was very much pushed by Kantorowicz in the 40s. and because it is about dates also, for this, the most important persons associated are Boltzmann and Shannon. By the way, next year will be the 100th anniversary of the birth of Shannon. And with gradient flows, this has a long, long history, but an important twist came when people started to do non-smooth gradient flows. How do you define the gradient flow of some energy which is not differentiable? And this had quite some, there was some applications, and people who pushed this to define schemes, approximation schemes to define gradient flow in non-smooth ways were in particular De Giorgi, Benilan, and then other people. And there's a whole big amount of works related to how to define gradient flows in a non-smooth context, one keyword being convexity. When you have some convexity type property, even without smoothness, you can always define something which has all the good properties of a gradient flow. So these are the four fields, and let's say that after some preliminary works, explicit links between them were made in particular in two papers. First, there was the paper by Jordan, Kinderlehrer, and Otto at the end of the 90s, making the link between optimal transport and information theory and gradient flows. And shortly after, there was a paper by Otto and myself making the link between optimal transport, information theory, and curvature. And this was somehow the start of the explicit study of this. I will give further references in a minute, in a moment, but just make one comment about this paper which I wrote with Felix Otto, and which for me was the start of a lot of activity, but also was the first time that there was explicit connection between Ricci curvature and the optimal transport. The paper occurred because at some point I was reading lecture notes by Michel Ledoux, and just 1 month after attending a seminar by Felix Otto. And then reading the lecture notes, I thought, there has to be a connection with the talk of Otto. And the connection was easy to find, maybe a quarter of an hour. It took us a couple of weeks to write the paper with Felix. So it's one of the papers that I wrote, which was the easiest to write. And to this day, this is my most quoted paper, which shows that impact of paper is not an increasing function of the work that you put in it. So let's go for optimal transport. So optimal transport is the following. You have a probability measure, mu0, and another probability measure, mu1, and the cost function, c, of x, y, start point, final point, and you ask about minimizing the double integral of c of xy, pi of dx dy, among all joint probability measures pi which have marginals mu0 and mu1. In other words, you ask about the minimum of the expected value of c of x0, x1 under the assumption that the law of xi is equal to mu I. So it's the most efficient way to couple the random variables x0 and x1, or if you want the laws, mu0 and mu1. If your cost function is equal to the square of the Euclidean norm, you know with squares you always have the best results, the problem becomes equivalent to finding the maximum correlation in the usual sense. So it has a natural probabilistic interpretation. Optimal transport is very nice for several reasons. First, there is a beautiful duality formula, which was found by Kantorovich, which says that this minimum is equal to the supremum of integral psi1 d mu1 minus integral psi0 d mu0 over all functions psi0, psi1, such that psi1 of y minus psi0 of x is bounded above by c of xy. Second, there is a very good notion of distance, which is associated with it. When you take cost function to be the distance to the power p, and the distance between two measures, mu0 and mu1, to be the value of the minimum to the power 1 over p, you have a nice notion of distance, and especially it's good for p equals 1 or p equals 2. Let's say L1 case, L2 case. In many applications, it's a more useful notion than total variation or LP norms or other notions of distance that you would put on measures. For instance, just to quote one field of application, in image computing, to assess the distance between two images, you will use typically these kind of distances. And the third thing is that there is a nice notion of interpolation, which comes with the optimal transport. Namely, if you have a start measure, which I represent like this, and a final measure, mu1, which I represent like this, and you find the optimal way to transport mu0 to mu1, then you can always interpret this as traveling along geodesics or some optimal trajectories for the cost, like if you are actually doing the transport. You say that this is at t equals 0, you say that this is at t equals 1, and when you look what it is on the way at some time t strictly between 0 and 1, it gives you an interpolation, some probability measure which will go smoothly or continuously from mu0 to mu1 as t goes from 0 to 1. And these notions are all connected, and you can find all this in a very good book which I wrote some years ago. And what can we say about the relation of optimal transport to the geometry problem? And I will give you the main contents now of the papers which I mentioned. So you retain for now, it's good because there is duality, there is a distance and an interpolation. By the way, for a long time, the main research about the subject was to find the duality formulas and to show that they are true in very, very general context. It's a research which has been going up to a few years ago only, and it was shown that the duality holds in amazing generality. And then, I should say this also. So for a long time, people were interested in generality of the duality since the time of Kantorovich. And then from the 80s, there was a new trend which emerged with researchers like Brenier, Ruschendorf, Gangbo, McCann, and others. So all this is end of the 80s, 90s, and it's research which has continued to this day, which was to characterize the optimal coupling. And to show, under certain assumptions, that it takes the form of a deterministic coupling, so something like y equals t of x, meaning that in the optimal way is to start from point x and go to some y which is determined by x, and under certain geometric characterizations of the optimal transport, typical result, one which is due to McCann at the end of the 90s, if we are on a manifold and mu0 is absolutely continuous with respect to volume measure, and the cost function is equal to the square of the distance, so this is what I call the L2 case, and then you ask, which is the best way to transport mu0 onto mu1? And the answer is that there is only one way, and that this way is to transport x at t of x, and with a t which has a special form, t of x is exponential of grad psi of x. This is the Riemannian exponential. I start from x. This is a vector grad psi of x. And I send the geodesic with initial velocity grad psi. And I keep it, I follow it up to time t equal 1. And this is the value of y, Riemannian exponential. So the theorem exactly tells you that there is only one way to optimal transport mu1 onto mu0. It takes the following form. It's the exponential of some grad psi. And moreover, whenever you find a transport which has this form, it is optimal if psi satisfies a certain geometric type condition which is reminiscent of convexity. And very precisely, the condition is that psi should satisfy, there exists some function zeta such that psi of x is supremum over all y of zeta of y minus distance xy square over 2. How to interpret this? This says that my psi is a supremum of something. It reminds you of convexity. Saying that a function is convex is to say that it is a supremum of affine functions. This is not an affine function, if you look at the dependence in x. However, it is given by a particular structure, here distance of xy square. And if we were Euclidean, the interaction between x and y, so to speak, would be in the form of a scalar product between x and y, and then we would be back to an affine function. So here we have a notion which is a generalization of the notion of convexity. And here, this psi and this zeta are kind of like the functions which I wrote in the duality, psi1 and psi0. Okay. So a lot of theorems were like this again, like let's characterize the value of the shape of the optimal function. And again, this is a research which lasted for years and years. So far, so good, hopefully. Now, the connection with the curvature. So, some landmarks. Jordan, Kinderlehrer, Otto, hugely important paper, showed that, so to speak, the gradient flow of the information function, gradient flow in the structure, in the geometry of L2 optimal transport is the heat equation. What does it mean? Gradient flow depends on gradient. Gradient depends on the geometry. If you change the geometry, you define the gradient. If you take for geometry in the space of probability measures the L2 optimal transport, then you have a gradient flow which is associated, which you define in non-smooth way, and that gradient flow will turn out to be the usual heat equation. So, remarkable connection between objects that we know very well, the entropy or the information, the heat equation, and the notion of gradient flow. What did we do with Felix Otto then? So it was the connection with Ricci. Ricci, non-negative, governs the convexity of H, the information, in the L2 optimal transportation geometry. You remember what I told you minutes ago? When you have a gradient flow of something, it's good if the something is convex. You can define all things, everything works. So it's kind of natural question. When do you have convexity? The suggestion and the conjecture which we made in there was that this Ricci bounded below by 0 was what would determine the convexity of H. And we gave arguments for this, and we proved some related stuff, and so on. This was checked by series of, in various papers. There was Cordero et Rosquin, McCann, and Schmuckenschläger. I write initials to avoid to have to write down explicitly Schmuckenschläger, which is always tricky. And there was Sturm and von Renesse, all this about the same time, putting in place the tools to study these links and to make and to prove the conjectures and so on. And so with this, there was the idea that there is a translation in terms of the information and the geometry of Ricci non-negative. A few years later, there was a paper of Lott and myself, and independently paper by Sturm, which suggested that this was the right way to do the synthetic theory of Ricci curvature, and that we should be able to devise a definition of Ricci curvature bounds, which was based only on optimal transport and entropy, so to speak. So I will explain this. Sometimes you find this in the literature now with the LSV spaces, which is a weak way to define, to state that the geometry has Ricci curvature bounded below by something. I will give other references in a moment, but now let's give a definition. Definition. Take X and D and nu. This is like the volume. This is like the geodesic distance. Okay, it has to be geodesic space, which means that any 2 points should be joined by a minimizing geodesic, things like this, but never mind. This, you think of this as playing the role of geodesic distance in Riemann geometry, and of this as playing the role of Riemann volume. And we will say that it is a CD, 0 infinity space, meaning that Ricci is bounded below by 0, and because it's infinity here, it means no restriction on the dimension. If for any mu0 and mu1 probability measures on X, there is mu t for t going from 0 to 1, an interpolation in the L2 sense, in the L2 optimal transport sense, such that h nu of mu t is bounded above by 1 minus t, h nu of mu 0, plus t, h nu of mu 1, for any t. So take this as a definition. Okay, this is the simplest of a number of variants. Simplest of many variants. What kinds of variants? Well, maybe you want to say it's for all interpolation rather than for one interpolation. Maybe you want to impose that something in here is finite. Maybe you want to, you are not satisfied with giving a meaning to CD 0 infinity. You want to cover also CD Kn. So you will twist the definition to introduce some dimension, and you find in the literature many of these variants. Let's say, for instance, For instance, you may replace, this is like a convexity inequality, okay? So replace the convexity, which is something like, let's write this H double dot is bounded below by 0, by something like H double dot is bounded below by K times the square distance, something like uniform convexity. And this is a way to introduce the K, which may be non-zero. Or maybe you replace the convexity by something like H double dot plus H dot square divided by N bounded below by 0. And this will be a way to introduce a capital N that will take into account the dimension. There are some variants, and in the literature, you find them under the name CD, CD star, CDE of Kn, depending on which precise choice you make. But the key idea is encapsulated in this particular case, the simplest of the definition. Ricci bounded below by 0, by definition, if you can find an interpolation which satisfies the convexity inequality for the information function. So it's always good to do definition, but then you have to prove something and to show that it is interesting. So here are some of the most important steps in the program. So the new, so to speak, definition is equivalent to the usual one if you are smooth. You remember at the very beginning of the talk, I recalled if you have convexity and you know a function is C2, then it's equivalent to have second derivative bounded below by 0 or the convexity inequality. Here also you have this. The new definition is very stable. And here the analog of pointwise convergence would be the Gromov-Hausdorff, or measured Gromov-Hausdorff topology. Meaning, typically, if you know that distances converge and volume converge, then you know that the concept converges too. And so far, it's the only known proof of showing that a sequence of manifolds of non-negative Ricci will converge to an object which has non-negative Ricci in some sense, without imposing strong notions of convergence like second-order derivatives of the metric or something like this. So the definition is stable, compatible with the Cartan-Alexandrov-Toponogov. This was shown by Anton Petrounin. You remember, Cartan-Alexandrov-Toponogov is weak notion of bound on the sectional curvature. Sectional curvature is a more precise concept than Ricci curvature, because Ricci is the sum of sectionals. So if you have a bound on the sectional, it should imply a bound on the Ricci. So if you have the property of fat triangles, it should imply the property of convexity of the information. And that is true indeed. It is also usable to prove some geometric consequences. Inequalities, functional inequalities. For instance, you can prove Sobolev inequalities and so on. It's also usable to have some heat equation. And this was contribution by Ambrosio, Gili, Savare, improved and re-improved. If you take a space which satisfies the Ricci curvature bound below as I wrote it, then automatically you can define a heat equation on it. And this heat equation, you can define it in two ways that will be equivalent, either as gradient flow in the usual L2 distance of the Dirichlet integral, or as gradient flow of the information functional in the L2 geometry. Probabilists know very well when they work in geometric setting that you need lower Ricci bounds even to prove that the flow is well defined. For instance, if you have an infinite manifold. What this result shows is that it's all you need. You don't need any smoothness, just lower bound on the Ricci curvature. Now, so far, so good. Then came a big dilemma, because new definition is very general. In particular, it is able to include Finsler geometries, Banach spaces, Finsler geometries, finite dimensional Banach spaces, and then it depends on your state if this is good or not good. You may say, okay, this is very good because it gives a way, for instance, to study isoperimetric inequalities, which are also Ricci curvature dependent for Finsler spaces in a unified way as to Riemannian spaces. But you may also not be happy because you may think that Finsler geometries is too wide. And it was pointed out at the time that maybe this notion is too general, in particular because it was grossly much wider than limits of manifold. And the answer to this was found by Ambrosio Gili Savare to define some intermediate refined notion, which I will call RCD for Riemannian CD, so that if you want, the situation is like this. These are Riemannian manifolds, say Ricci bounded below by 0. These are Riemannian CD spaces, and these are CD spaces. These are the spaces I told you about. This is the class of Riemannian manifolds, and this is the RCD class, which is intermediate between them, and which does not contain the Finsler geometries. And what is the RCD class? It is made of the CD criterion plus the fact that the heat equation should be linear. In general, heat equation is nonlinear, and it's in the order of things. But if you ask that it be linear, then you define a subclass here of the CD spaces, which again is stable, compatible, usable, etc., but which does not include the Finsler. In this class, at least under some restrictions, you need to be careful about the definition, you need to impose some non-branching condition and so on. You are able to reprove almost everything that is known about this class, Riemannian manifolds. And this was done in particular by Erbach, Kuwada, and Sturm, Ambrosio Gili Savare. You can prove a Bochner formula, you can define some Laplace operator in some sense. You can have all the inequalities which are classical for Riemannian manifolds. It's not yet clear if this class is really wider than the class of limits of this, but it is in spirit rather close. And so you can satisfy at the same time people who are happy to include the Finsler and people who are not happy. Let's conclude with a list of directions and outcomes. You may also say, why do we do all this? And which are then outcomes outside of the theory? Here are some outcomes. So, some outcomes. First, as I told you, new construction of heat equation, which is so general, and it's not necessarily the result which is of interest to you, but the method. Now I can tell you, whenever you have a space with some natural measure, you want to construct a heat equation, try the gradient flow of the information if there is a well-defined information. And it may be just what you are looking for. Some other outcomes are new proofs of classical geometric inequalities, which were proven, which were obtained in the course of studying this. Two of the main examples were a new proof of the L1 Poincaré inequality and a new proof of the Lévy-Gromov isoperimetric inequality. I will not write explicitly the Lévy-Gromov, but it's kind of the most, let's say, at the same time beautiful and powerful isoperimetric inequality involving Ricci curvature. It tells you that if Ricci curvature is positive, then isoperimetric inequality in your space is not worse than isoperimetric inequality in a reference sphere which has Ricci curvature bounded above by the Ricci curvature of the geometry you are in. It says that if you have lower bound on the Ricci curvature in positive curvature, then you can compare your inequalities to inequalities on the sphere. Very powerful. And so far, all known proofs were terrible, meaning you have to involve subtle regularity theorems for a kind of regularity that you find in geometric measure theory and in these big papers by Almgren and other people in this field. And now, for first time, playing with this idea, Cavaletti and Mondino found a proof which is just right, just as you would like to be, which applies in all this class, at least if non-branching, and which does not involve any fine study of smoothness, but just optimal transport, the distances and the volume, and in an interesting twist, involves both the L2 and the L1 optimal transport. This was a surprise because apart from this, all the theory was based on L2 optimal transport. Anyway, this proof is shorter, more comprehensible, and conveys some meaning. Some proofs also, some progress in metric analysis. To fulfill this program, Ambrosio, Gili, Savare, and others had to develop the theory of Sobolev spaces and metric spaces, Hamilton-Jacobi equation in Sobolev spaces because it's related to geodesics, heat equation in metric spaces, and a lot of problems making some of the most important advances since the studies by Chigger some time ago about metric analysis. Some progress about Finsler geometries, new notions of curvature, new inequalities, and new heuristics in statistical physics. For instance, you can reinterpret heat equation in a different way with this, as I said, but also some hydrodynamic limits, and in geometry in general. For instance, there was a work recently showing that if you have a manifold of non-negative Ricci curvature, then automatically there is a universal bound on the ratios of the successive eigenvalues to the first eigenvalue. And this bound depends on nothing, independent on the dimension, independent of diameter, anything. And the first proof was obtained by playing with the interpretation of Ricci curvature and entropy. And also some efforts in direction to understanding flows and stochastic evolutions of geometries and probabilities of geometries, let's say. Let's quote for this work by Lott and Topping to rewrite part of the Perelman proof of Poincaré conjecture using interpretation in terms of optimal transport. Let us quote work by Sturm, by Kuwada on defining Brownian motion in spaces like in these general non-smooth spaces, works to define good notions of Gibbs measures on the space of probabilities, evolution of the geometries that would play the role that eventually could play the role of Ricci flow. And this will be all. Let me mention also, which for me was a really nice twist, the idea, the way to do some discrete curvature. So, one advantage of synthetic geometry is that you can play around with the definitions and properties without being too much attached to the regularity. So imagine you are given the task to define the curvature of a discrete space. If you try the definition which I gave you for curvature, you are doomed. But if you try the definition with the entropy, you can come up with many possibilities. Let's work with an approximate geodesic rather than a true geodesic. Let's use the usual measure, the natural measure, which is associated with discrete counting. Let's use this or that notion. You can come up with various ways. Sturm and Bonsioka, Olivier, myself, a number of people did this. There were some beautiful works in this direction, but anyway, now there is in particular a way to define what it means for discrete space to have Ricci curvature bounded below. And this, I said, was very nice twist because I remember vividly a seminar which was held in Institut Poincaré at the end of the 90s, and there was Dan Struck asking the question at the end of a seminar, what is Ricci curvature of the hypercube? Hypercube is this, -1, 1 to the power n. Just the two-point discrete space, you raise it to the power n. What does it mean, Ricci curvature of this? Obviously nothing. Now we know exactly what it means, and we know that this space has Ricci curvature bounded below by 1 over 2n, and that this coefficient is the optimal, and we know what inequalities we can deduce from this. So in a way, managed to put start putting curvature arguments, which are typically continuous, in the discrete world. And okay, how to say it? This was cool. Okay, thank you.
Thank you very much for this wonderful panorama of optimal transport and geometry. So there's very limited time, maybe for very brief questions, if there are. So otherwise, might be a good idea to postpone the questions.
As I said, in South Korea, I discovered when there are panels with kids and so on, they offer presents to those who ask questions first, like dedicated books.
Okay.
Yes. Very quick, Theo.
So Theo.
Microphone here.
You have any guess what the structure theory will give concerning tangent spaces? Is there a constant dimension for all
okay.
points of a given RCD space?
So this is a beautiful question. Let me explain it because it's interesting. You remember, so first to put the problem in perspective, you remember when I said about convexity, you may define it for C2 functions, or you may define it for completely non-smooth functions in this other way. It turns out, if you define it in that other way, assuming no smoothness, automatically implies some smoothness. And the famous Alexandrov theorem tells you that the convex function automatically is almost everywhere twice differentiable. So you have automatically some regularity in there. And if you look at spaces with lower bound on the sectional curvature, then also you have structure theorems. The best ones were due to Perelman. You know that there is tangent space almost everywhere, some kind of twice, I even think some kind of twice differentiability, right, almost everywhere. So now the question for Ricci curvature is more tricky, but it can be, there are some results already of rectifiability in this class. And so far, people are able to prove, I think there's Naber and Mondino, able to prove that it's rectifiable almost everywhere, but they don't know if the dimension is independent of the point. That would be beautiful if essentially, up to some part maybe that you throw out, it would be, you could define a real dimension in the sense of rectifiability for these spaces. And it would be something like, don't assume any irregularity, but automatically it comes from the curvature condition. I think we can let these guys work. And they seem to have good program. But let's be hopeful and say that, yes, I believe there is a constant dimension.
Okay.